I hope that's okay with you.
Yeah. Okay.
So yes, I got it.
Somebody should get on.
Okay. The starting point is something that everyone probably knows, is that since the times of Reynolds, it is known that the motion can be very wild or very laminar or very easy, smooth or not smooth. And there is one parameter which is very important, which is not the viscosity, but what is called the adimensional Reynolds number. And the criterion to have stable flows or unstable flows, the simplest one concerns how big is this number, this Reynolds number. So you remember that the viscosity is generally very small. So you have something which is very small on the denominator. So in real applications, the Reynolds number is very large. Okay, and the Kolmogorov theory from 1941 tells you that the number of degrees of freedom that you need to fully resolve the fluid, the motion of all the scales of the fluid, is in 3 dimensions of the order of the Reynolds to the power 9/4. So remember, the Reynolds is already a big number, and then you need this number of points, which is Reynolds to the number 9/4. And this gives you that for realistic flows like geophysics or several applications, the order of the Reynolds number could be up to 10 to the 18, but starting even an airplane or a car has a Reynolds number which is of the order of some millions. So you have a lot of points, and the main difficulty is that you need a very large data set of memory, so you cannot store all the data, and so a direct numerical simulation was impossible at the time of von Neumann, but is impossible also in our times. Okay, so in order to do something significant, one possible idea is that one is decomposing the flow into a mean part, V bar, and what remains, which are the fluctuations. So the mean flow is some philosophical idea is that the mean flow is capturing the relevant part of the motion. And so one would like to have an equation describing what is doing V prime over V bar in order to solve only V bar, and V bar contains only large scales, so something that is really computable. Okay, so there are some fundamental issues. If this is sound, if how these averages are defined, because there are several ways of defining space averages, time averages, statistical averages, and so on. And then one would like to write some equations for these approximate equations for this V bar. Okay, for mathematicians, the basic goal would be I write an equation only for V bar, and then I would like to have a system of PDEs which is good and which is probably giving me some information about the real averages of the flow. And the modern approach, starting in the 60s with Smagorinsky, Jacquions, and Helmholtz, they were more or less doing all the same thing. So they were thinking that using something coming from the so-called Bushnell's hypothesis, that the effect of the fluctuations on the mean flow is to increase the viscosity. And so they were adding a p Laplacian, which is a monotone operator, to the equations and see if the theory can be done with this system. And so the model that has been studied by Smagorinsky, but in fact it was used earlier by von Neumann and Richtmeier 10 years before, but it was something classified on the Manhattan project, is that you add some this is extra dissipative term, and this parameter L squared here is a length. So it is the Prandtl length, and determines the smallest scale that you are willing to resolve with this set of equations. And this model has been tested in several cases. But a big limitation is that this model contains only one length, the Prandtl length. And so you are supposing in a too optimistic way that the flow is homogeneous. So the properties are not changing from one part to the other part of the domain. And so if you are doing what is called homogeneous turbulence far away from the boundary or in the periodic setting, then the results are reasonable. If you are going through the boundary, and so if you have a boundary layer, then this could not work because you have a fixed length, and when you are approaching the boundary, some different temperature, taking into account of the distance from the boundary will appear. Okay, so the classical theory is not done. In fact, one has not to use this equation because the gradient of V is not a quantity which is invariant by changing the system of reference. So the gradient could be seen differently if the observer is changing. And so the right quantity to be used is the deformation, so the symmetric part. But this will not change too much the mathematical properties. If you have a kind of Korn inequality, then the properties are more or less the same. But there are some very fine analytical properties of the operators depending if you have the full gradient or if you have only the symmetric gradient that appear. So in terms of the regularity of the solution, there are some differences, and people like Asia, Chunky, Rushka, and others are still studying what happens if you change the vectorial problem having the gradient or the deformation tensor. But in just to give a very rough idea, the basic tool that one has to use is the fact that the operator is monotone. And so when you have the Galerkin approximation of the solution, then you can show that they converge to a solution of the limit problem because you have the monotonicity. So the fact that this operator is nonlinear, so here there is a modulus of V and dV, which is not linear, is handled by using the fact that the operator is monotone. And this is very important for what comes later. And in fact, Latizestria was not studying exactly this model with power 1 here, but she was studying the problem with P minus 2, where P can be any parameter larger than 2, because her idea was that for large P, you have global existence, and so she was trying to pass the limit as P is going to 2 in order to prove possibly regularity for the Navier-Stokes equation, something that could not be done. So there is a limit of this approach that stops at P, which is 11/5. But nevertheless, the fact that you are modeling the extra viscosity in this way became a problem of mathematical importance for itself, because it's the basic way of modeling non-Newtonian fluids. So if you have P larger than 2 or P smaller than 2, then it happens that this term is increasing or decreasing as the deformation increases. And so you can have shear thinning or shear thickening fluid. So this became, beside turbulence, a mathematical problem of interest by itself in the class of non-Newtonian fluids like blood or mixtures of different fluids and so on. Okay, the basic problem of the Smagorinsky model is that you have a single length, and this fact that you have a single length does not work fine when you have a boundary. So if you take a very academic test, you have the flow and you have an object that is what is called a phase lattice step. Then if you do a direct simulation, you see a lot of vortices behind the step. If you use the Smagorinsky model, you don't see these vortices because the model is not able to capture what happens near to the boundary. So it is too dissipative and the small structures are destroyed. So this is a big limitation of using the Smagorinsky model in presence of boundaries. Okay, but this was known since the very beginning of the history. And the first trial to make the model working even close to the boundary comes from the work of Van Driest, but also von Karman. They were if you have a plate or a channel, and z is the distance from the plate, they understood that you have to model this length by something which is the distance from the boundary itself. So, this is the so-called von Karman equation, and k is a constant that can be computed. And so you see that this extra term, this part is the extra viscosity, and this term is going to zero as z is going to zero. So you have a vanishing viscosity up to the when you touch the boundary. So you have a sort of weighted problem in which the effects, the extra smoothing effects, disappear when you are getting closer and closer to the boundary. Okay.
So again, what is the reason behind, like from what again? What is the reason from modeling point of view that you put that it vanishes at the boundary? That extra viscosity, yeah. Yeah. Again, why you want?
The reason is that we know from experiments that if L is not going to zero, then you have too much dissipation near the boundary, and so the effects in the boundary layer are destroyed. And so you don't see what happens at that point. So it works well far away.
Meaning that the Prandtl boundary layer has already very huge gradients.
Yes.
So then if you add that term, it will kill them.
Yes.
Kill them.
You have a too big viscosity, which is not realistic with the properties of the flow near to the boundary. Yeah. And this practically any kind of boundary layer which is laminar, like even Blausius, is completely destroyed because the grades are big enough. Okay, so the reason is that one would like to have a quantity. So why they arrive to this problem having the distance from the boundary and the gradient velocity. So the idea is that you must have something which is proportional to the mixing length and to the kinetic energy of the fluctuations, at least in some approximation. And so together with the Smagorinsky model in 1978, Baldwin and Lomax proposed another model, which is probably more accurate in terms of reconstructing what happens to the rotation or to the vorticity near to the boundary. So instead of having here the deformation tensor, they understood that putting the curve, this gives you something which is weighting not the deformation, but the local rotation of the fluid. So again, there is a coefficient which depends on the distance from the boundary, and then the vorticity. And so if you are using the velocity and vorticity formulation, then one has to consider the stress tensor as a rotational stress tensor. So instead of having the divergence, you must have the curl of this quantity. Remembering that if this is a constant, the curl of the curve is minus the Laplacian for divergence-free vector field. So if the turbulent viscosity is constant, you still have the same equations. Otherwise, you have something which is written consistently in a rotational way. And so the system that Baldwin and Lomax considered is the following. You have the standard Navier-Stokes equation, then you have this extra term with d, which is the distance from the boundary. Okay, and generally, so remember that this number, if it is written in a non-dimensional form, is very small, so this can be disregarded. And also the mathematical properties are clearly much more complicated if you have mu zero, which is vanishing, or put it in another way. If you want to understand what is really the role of this term and what are the properties which are independent of the viscosity, you must have a theory which is not using mu zero in the construction and in determination of the regularity of the solutions. And just to let you understand why these numbers, remember that in the region where where you have large eddies, so large vortices, the velocity changes are order of 1. While in the regions where the smaller eddies are created, then you have something which is of the order of 1 of the radius of these small structures. And so the turbulent viscosity would be of this order, in order of this squared, where the vorticity is not too large. But it becomes smaller in the regions where the vorticity becomes larger. And this is important because one can study also more general methods which are still consistent from the mathematical point of view and also from the physical point of view. So remember that this guy was considering here p minus 2 for general p. So one wants to understand if the Kolmogorov theory predicts what is the coefficient that you have to put here. So here we have a length, and this length must be to some power. And the case that Baldwin and Lomax considered was p equal to 3, which means that this is power 1. And this is 3 minus 1, which is power 2. So this squared omega to the power 1. Remember that, because we will see later why this is very critical, that the critical value is for alpha, so for the power of the length is p minus 1. And this is very important from something that comes from harmonic analysis. And so from the point of view of the dimensions, the Baldwin and Lomax model, you have t squared omega, and so this has the correct dimensions for the viscosity. So if you are changing the exponents, you cannot do this changing the exponents. So this is the only way that you can construct a viscosity by using length and vorticity. So if you want to have a model with p, and p is different from 3, you must have another quantity. And from the dimensional point of view, the third choice is that you use what is called the friction velocity. So it is the square root of the stress at the wall divided eventually by the density. So this is something which has really the dimensions of a velocity. So the turbulent viscosity should be omega to the power p minus 2, some power of t, and then you have this velocity with some power. So if you try to discover which are the dimensions, the only consistent solution is that alpha is p minus 1 and theta is 3 minus p. So the correct exponent for the length, for the power of the length is exactly p minus 1. So there are two different ways of seeing this, but both produce the same result. So the correct generalization is that you have the friction velocity d to the power p minus 1 and omega to the power p minus 2. Okay. So the system that we considered is then the following. So alpha should be now 2, because here we are putting p minus 1 and p is 3. And now I will explain why alpha, which is equal to 2, cannot be used. So the equations are rewritten in a fully rotational form. So instead of having the standard convection, we write it as omega cross v, and then there is a part which enters the pressure, which is the so-called Bernoulli pressure. Okay, so the theorem that we proved is the following: that if L is the distance from the boundary, and
sorry, the pressure in your model is a function of v and omega, or it's given as a
no. The pressure is the pressure plus b squared half, but it's not given. It's an unclonal problem. So this is still the Lagrange multiplier to the fact that divergence of v is 0, and automatically also divergence of omega is 0. And what is important is that this model still keeps that the velocity is 0 around you. So the model is consistent with the fact that you have Dirichlet conditions, and the fact that L is going to 0 when you touch the boundary will be consistent also with this, but in a non-trivial way. Okay, so the result that we proved is the following: that if the power is not the critical one, but it is any smaller than 2, and if the external force is reasonable, then there exists a weak solution which is continuous in L2, so the standard energy estimate, and the first derivative in L3, they belong to this weighted space, which means that it is not gradient in L3, but it is that the omega to the power 3 weighted with some function is bounded. So this is a standard setting in which you have weighted Sobolev spaces. Okay, what is important is that this is the energy estimate, and in fact it's not formal. We can prove that this is a real equality, it's not an inequality. Here there is only the vorticity, but in the theorem we have the full gradient. So we are able to control from the vorticity also all the derivatives of the velocity, which is non-trivial, at least in this setting. Why, even if this is trivial in L2, but in the setting of weighted spaces, this becomes non-trivial. And the limitation on the fact that alpha, this power, is smaller than 2, is for who knows these things related to the fact that this is not a Mukhanov weight when alpha is equal to 2 or larger than 2. Yes, this is harmonic analysis. Yes, this is why things are required this way. Okay, just to give you the flavor of the techniques, the standard result by the 60s is that for the static problem, if you have an operator which is bounded, semi-continuous, monotone, coercive, then you have existence. So this is the theory of Lyons and Minty Browder. So this is something from the 60s. And this works for the steady problem. Then a powerful generalization came with the work of Bresis, using what is called pseudo-monotonicity, which has some definition, but for what are interesting for you is the following, that if you have an operator which is monotone and continuous, and you add some compact operator, it's not anymore monotone, but it fills in the setting of pseudo-monotone. So if you add these two operators, then the theory can work. And for us, this would be the P Laplacian or this Baldwin Lomax operator, and this B is the convective term. So one has to show that the convective term is compact in some space. Okay. The difficulty in our problem, which is an evolution problem, is that one has to define the theory space-time, and the theory space-time is more complex because one has to define what is a Bochner monotonicity, because one is using Bochner spaces, which are spaces from the real line with values in some Banach space. So the theory is not hard, but one has to rewrite the problem as this calligraphy, this course, black U is a function of space-time, and so you have to define the problem space-time at the same moment. And so practically you have to show that this operator, which is acting now space-time, is still monotone, coercive, and has the properties that allow us to give the existence. And this part, yeah, I can skip this, but the interesting point is that if you consider the calligraphic operator, which is the space-time extension, then you can show that it has the good properties if you are able to show that the steady operator that is written here has the good properties time by time. So practically, one can show that if the operator is time by time with good properties, then this is translated into space-time good properties. So practically, we have only to show that the operator of Baldwin Lomax, the one with A, has this growth, and it is coercive. So these are the two things that we can check time by time. Okay. Now we will see why the exponent alpha p minus 1 or larger becomes an issue. So this is the general definition of weighted space. So you have LP and then you have a weight, some function rho which is non-negative. And the first property is that if this weight rho is the distance from the boundary, then this function go into L1 or L1 log only if the power of alpha is smaller than p minus 1. So if you want to work with standard distributions, you need alpha smaller than p minus 1. Then the other property is that in W1P0, you can consider this as an equivalent norm again only if alpha is smaller than p minus 1. So the Poincare inequality requires still this limitation on the exponent. And okay, in fact, all the properties come from this Mukhenov class, and practically if the weight that you put in your the vector space is d to some to power alpha, and if the domain is at least Lipschitz, then this requires that alpha must be smaller than p minus 1. And also, and this is the point that I stressed at the very beginning, by using the Ostavar law, you can show that if you are able to control the curve weighted, then you control all the derivatives weighted, but for all p, which are between 1 and infinity, but again, these powers must be smaller than p minus 1. So it enters several times that the critical exponent cannot be reached. And the other tools that we need are the Hardy and the Caffarelli-Cohen inequalities. So this is an inequality that tells you that you can control the p norm and the q norm, and if you have no weight, this is exactly the Sobolev embedding. So this is a generalization of the Sobolev embedding when you have the distance from the boundary. And in the original paper, Caffarelli-Cohen considered only not this function, but the distance from the origin. So this is not a famous Caffarelli-Cohen paper. So it is another one that appeared 2 years later, which is connected with different tools. Okay, so the two things that we use is this inequality and the Hardy inequality, which tells you that you can have the same exponent, but the powers of the weight change in this way. And again, this is valid only if alpha is not p minus 1. Okay, so the basic tools are now this operator is monotone independent of the fact that we have here the velocity, the deformation of the velocity of the vorticity. And this works for any function. So at this point, the limitation on alpha is not present. But the real difficulty comes from the fact that if this denotes u grad u or omega times u, we must show that the nonlinear part of the equations is monotone. Is compact. And just to tell you why it works, practically you start with this quantity that you have to bound. And this quantity has no weights inside. So you have to produce the weight to go with the curve because you are controlling only the weighted node of the curve. And then you have to multiply and divide, and you must be able to bound these terms with the same one that we have from the equations. Okay. So the theory is just checking that something works, and in fact, this works also for all p larger than 3. So we have done for p equal to 3, which means that p minus 1 is 1. But if you take p larger, and if alpha is still not p minus 1, then the theory works in the same way. The difficulty is that we cannot go below 3. So the Baldwin Lomax model started with p, which is equal to 3. Large p is okay, but smaller p are not. So when p becomes smaller than 3, you are not able to bound the convective term in a precise way. So this requires other exponents. So which means that the critical exponent to have existence theory is exactly 3. While for the in the case without weight, the exponent is much smaller. It is 11/5. So this explains again that these are something very intrinsic to the problem. Okay, now let's go to some modeling part to understand if this model is satisfactory or not. So the theory can be done, it is okay, but it is known since the work of Speziale, Lomax, Harding, and others that when you do less modeling and you are in a rotational frame, which is mostly the case for several geophysics applications, and this frame is changing under non-constant velocity, then the modeling probably is not so nice. And in fact, the main problem is the following: that the mean velocity transforms like the standard velocity. So you have the Coriolis force, the centrifugal force, and so on. You want to understand if the Reynolds stress tensor, which is the average of the fluctuations, is transforming in the same way or not. So if there are constraints that you have to put on the system. And what is known is that the Reynolds stress tensor can depend on the vorticity. Capital omega is the velocity, the rotational velocity of the system. So the Reynolds stress tensor should be invariant for translations, but should be affected only by this quantity in case of rotation. So it can depend only on omega plus the rotation of the system. So if you have other quantities, these are not consistent with the fact that you are writing equations which are different in different system of references. So the other limitation is that the change of the frame-dependent effects must vanish in the case of 2D problem. This is why in 2D, since you have a domain, the motion is on the plane and the angular velocity is vertical, then the rotation can become via the stream function a gradient of pressure. And so the system has not to see that there is a rotation, at least when you write correctly. And also, the Reynolds stress tensor should be consistent with the Taylor-Proudman theorem. So you want that if the rotation is very large, the motion should become close to the two-dimensional case. So the motion should become stratified. And this is not working with the Smagorinsky model, because the Smagorinsky model depends on the deformation tensor, which is frame invariant, but is not depending on the velocity. So, on the angular velocity. So, if you start rotating, this viscosity is not seeing that the system is rotating. So, it's not consistent with the fact that if there is big rotation, the motion becomes stratified, and also is not capable of understanding if the problem is 2D or 3D. The equation, the heavy viscosity is okay, but it is too rough. So what happens with the Baldwin and Lomax? Baldwin and Lomax depend on the vorticity, and then when the system is rotating, it depends on the vorticity plus the angular velocity of the system. So in terms of invariance, is okay. The problem is that when omega becomes large, the eddy viscosity becomes infinite. And so you have too much dissipation. And so the Baldwin and Lomax model is not capable of showing that in some even formal sense, when you have high rotation, the system becomes 2D. So it should be the opposite. This should be 0, not infinite, when omega is not. So from this point of view, also the model of Baldwin Lomax is not okay. Okay, but they have been used for several years, and for mathematicians, they are okay because they fit into the theory that we are able to do with monotone operators. So if you have a general nonlinear operator with no structure, then you are not able to produce any theorem of existence. So this is why they were so studied in the mathematical community. Okay, so the major problem is that when you have a single viscosity, a single eddy viscosity, this probably is not representing well what happens if the flow is rotating near solid walls, transitional regimes, and so on. And so people start studying some selective or dynamic eddy viscosity model. So the eddy viscosity should change point by point depending on what is happening to the fluid in that point. And the first idea, and this is probably the idea of Baldwin Lomax, is that the extra stress tensor, so the eddy viscosity, should work or be active only when you have high vortex activity. But this high vortex activity is very vague. For mathematician, is probably, okay, I measure the vorticity, I see where it is large, and then this is a region of high vortex activity. So the problem is that vorticity large does not mean anything. So in the shear flow, you have vorticity, but you don't have rotation. So something that would be more interesting is to understand where the fluid is locally rotating. And this measure is not only the vorticity, but is something more sophisticated. And in fact, at least in the 2D case, Okubo and Weiss started considering a different criterion. So they took the trace of the square of the gradient, and then in 2D, if this is negative, this means that you have an elliptical point. So the particles are rotating. But in 3D, this is much more complicated. And Moyne and others, they introduced what is called the Q criterion. So the Q criterion is such that you have the difference between the rotation and the deformation. When this number is large, then you are thinking that at that point something is happening, because this is taking into account that the fluid is deforming. This is taking into account that the fluid is rotating. And so when this number is large, then probably there is a high vortex activity. So the problem is that this criterion is not universal. So there are fluids where you have vortices, and this tells you that you have a large number. But if you change the system of reference, another observer can see that you don't have large numbers. And so the problem is related with some a problem typical of geophysics, which is the vortex identification. So the identification of where the rotation is taking place. And okay, again, omega, the vorticity is not a measure of this, because the laminar boundary layer is irrotational. So it has rotation, has vorticity, but it is irrotational at the end. And the vorticity also does not represent rotation, because if you have a rigid body which is rotating solidal, vorticity is not zero, but then this is something which is rigid. So the two things are not so straight as they are. So that the fact that vorticity is a good quantity came from the theory of Helmholtz and Kelvin and so on, because it is a property which is transported by streamlines. So the idea is that probably the Random quantity would be a better indication of where rotation is taking place, not an Eulerian quantity. And in fact, to illustrate this problem, let's see what people has done with this situation. So you have the sea, and you have satellites like Evisodata, in which you have the height of the water, and you want to understand if the height of the water can be related with the fact that there is vorticity or not. And a typical example is the Woolwich leakage. So you have the water exiting from this part, and this is what you see from the satellite. So these are the difference of height of the water, and you see that here you have really something that looks like vortices that are spreading out from the south of South Africa. But so this is what really people see from the measurement. So this is difference, the relative difference of velocities taken from some month. And so you want to understand if this can be related to vorticity. And in fact, Harder and others, they consider a way of reconstructing from these images taken from pictures, what are the coherent regions which are rotating. And they developed a very complicated algorithm in order to keep trace of this Lagrangian modification of the eddies.
So can I ask a question? If you go back, can you explain the picture? Like, go back again. Yeah, here. So
yes.
The picture is.
Okay.
I'm not understanding what the color means.
Oh, okay. The color means the larger or smaller velocity. So this is what people would like to understand. And so
it's not the flow. It's
no, it's not the flow. Is only large and small velocity.
And large and small velocity, yes. But it's not telling anything.
Kinetic energy, right?
Sorry?
That should be the kinetic energy.
Yes, kinetic energy. So large velocity is kinetic.
So
but it has nothing to do with the direction. The direction is
it's not no.
V squared.
Yes,
so
V squared, but probably where you have these light regions, the kinetic energy is large, and these are circular regions. So probably you think that the fluid is rotating, but it is not an indication.
Okay, so the white means that large velocity.
Yes.
And the blue
small velocity, so
small velocity.
So close to steady. And
so there are like large, but there are large velocities in the south, like close to South Africa.
You see the boundary currents with that jet-like, and these boundary currents break down in vortices, those rings.
Yeah.
Also, this is the other western current, and this is what is the name of the one coming from?
The Brazilian current. Brazilian current.
I have a question. Can you compare your models with exact solutions of Navier-Stokes equations in the regions of high vorticity, which is vortex sheets and vortex lines? There are exact explicit formulas, vorticity drawing, and you could compare.
Yes, you could do, but this is not enough. So people have tried to take data from turbulent channel flow, and the different criteria give you different indication of where the vorticity is. So
I'm talking about exact analytical solutions, not about experimental data.
Exact analytical solutions are generally too easy for testing. So you don't have solutions which are complex enough to make this comparison. So for the boundary layer solution, this tells you that you have no rotation.
Berger's vortex is not complex enough. There's
No.
a vorticity which goes to infinity, and it's
No, it's not complex enough because you have a single vortex. Things are interesting when you have two that are interacting, for instance. In that case, okay, this is what people that I told explained to me. And okay, this is the first picture. The second picture is really measure of the height of the water. So from from the zero level, and so this is what is taken by satellites. And so from this picture, you would like to reconstruct the velocity, and you want to reconstruct if there is rotation or not. Rotation.
So the height of the water from
the reference level.
So there are areas where it is like, but how large is that? Like a few centimeters or meters?
No, that's South Africa.
What?
Yes. See, this is South Africa.
Yes.
I could be 2 meters, I think.
Huh?
1 meter, 2 meters.
Oh, the height.
Yeah.
The height could be 1 meter is really big.
Yeah.
Half a centimeter. Usually half a meter. Those are
Yeah.
centimeters.
So 50 meters, and so alpha meter is the regions in the, it is Capo di Buona Speranza. Yes. Yeah.
Good hope, yeah.
Yeah, good hope.
South of
Yeah.
Cape Gallas.
Okay, so
I was thinking
you get-
that
you get the
area
velocity.
should move, like it's not the same.
Yeah, it's moving. Okay, but
So these are like waves, right?
yeah,
So it's
these are,
just
in
waves.
fact, these are like waves. And in fact,
the important thing is that the height gives you the velocity at leading order, because at leading order, hydrostatic pressure
Yeah.
balances Coriolis.
yeah, so
And so you can just solve for velocity. If you, I mean, the height gives you the hydrostatic pressure, and then you solve for velocity, and then you have the leading order approximation.
So this is the system that is using the beta plane approximation. Yes. And so what they have done is that they were able, from the images taken from yields, to reconstruct how this eddies shed and propagate inside the flow. And let me see if this is. Okay, so with this complicated, with some complicated algorithm, they were able to trace the Lagrangian eddies, and the difference between the blue and the green spot is that you have what is called the center of this eddy, and you are trying to trace the center. So one is what is obtained by Eulerian approximation. So you are practically freezing the velocity at some time, and the other is that is obtained really following the fluid. So the computations are much more difficult for the second one. But this requires computations of hours, and you reconstruct some eddies, how they are shedding for days after the Agulhas language. So, but this cannot be used in so you have images and you can reconstruct where is the vortex. So in some simulation, you would like to have a way to detect where the vorticity is large in real time in order to use it as an eddy viscosity. And so these things are too complicated. So another model that I am studying now, and that requires testing even on simple flows, is the following. So the gradient of the velocity is generally interpreted as a deformation plus a rotation, even if these are not the good words, because the omega should be decomposed into a real vorticity and the part which is non-vortical. So, like in a boundary layer case, we have vorticity, but this part must be disregarded because that part is just shear flow. It's not taking into account that anything is rotating. So one would like to decompose the vorticity in two parts. The part which is rotation and the remainder. And this part, the part which is a real indication of rotation, is that you should identify some direction, and then the angular velocity will enter in this way. And when omega is 0, then you have a rigid rotation. And a rotational flow when omega is equal to 1. So a way to identify this angle is that you should know the local properties of the flow, and you should evaluate the eigenvalues of the deformation tensor. So, but this is again too hard computational from the computational point of view. You cannot do for each point looking if there are complex eigenvalues in such a way that tells you that there is some rotation. So a way to probably overcome this problem, and that has been proposed recently by Liu and co-workers, is that this object, which is the indication of the rotation, which is a number between 0 and 1, should be approximated like the vorticity divided by the deformation plus the vorticity, modulus the Frobenius norm of both of them. So you see that this is a number between 0 and 1. When omega is 0, then this number is 0. And when omega becomes extremely large, infinite, this goes towards 1. And in fact, if you have a rigid body with uniform angular velocity, then du is 0. And so this gives you a perfect understanding of the fact that you have no rotation in the correct sense of view. So the body is rotating in a solidal way, but is not micro-rotating.
How did they guess this approximation?
They guessed this approximation because they were thinking, okay, why you have the numerator and the sum of the formation becomes the denominator. So the idea is that the two quantities are not independent because the sum is the full gradient. So there is a drain from one quantity to the other one. So the fact that you are adding the sum is that you are taking into account how big is this part compared to this one. And this is an indication if you have a deformation or if you have rotation. And this is weighted in this strange way. One is thinking that the opposite would be better, so having du minus omega, but in fact it seems that at least from some analysis of easy configuration like a rotation of a rigid body or a shear flow, then this is a natural indication of the size of this omega. So this is only an approximation, and this also has some ideas that when you have a vertical flow, the dissipation is smaller in some vague sense. So the idea is that when you have a rotation, then the rotation state is more stable or is more generic. So the laminar flow is very unstable. So minimal perturbation gives you to something which is rotating and turbulent. When you have something which is turbulent, then this remains. You see much more in the fluid. And so this is why the indication that the eddy viscosity should be done in this way. Okay, so now the mathematical.
So I mean, in a sense, rotation stabilizes the flow.
Yes, yes, but not only at the macroscopic level, but also microscopic. So this is why this is the indication. So the difficulty is that if this one becomes the eddy viscosity, then you don't have anymore a monotone. So all the theory that we are using is not working. So you have something, and you have only weak convergence for these quantities, and probably you are not able to pass the limit. Other tools must be developed, or the equation must have some other approximations. But this is the new frontier of having eddy viscosity models which are taking into account of the rotation of the fluid in some computable way, not only for testing a posteriori on data, but also for constructing models that could be used to produce what is called simulations and predictions of the flow. Okay, okay, but this part is not relevant. I think that I can stop here. Any questions?
I just want to make a simple comment. If kind of philosophically the eddy viscosity is the idea to reproduce the effects of large vorticity, replacing viscosity and dissipation coming from large vorticity without viscous term, that exactly happens in the Burger's vortex. It's not simple from that point of view.
No, in this sense, you are right. No, the geometry is probably too simple to see if these criteria,
and
which
that's
are
my
pretty,
second comment. Yeah. I recently published a paper and talked about it here, where I considered the circular Burger's vortex a singular ring, and there's a vortex sheet inside. There's much less trivial solution with non-trivial topology, and you could study this as I will send you the paper.
Yes. Yeah, thank you. Because the other case that is typical in these problems is the Taylor ring vortex. This is a case in which the streamlines of the vorticity are very banded, and so this is considered as a potential source of singularities. But for that vortex, you don't have an explicit you know the initial datum, but you don't know for all time. So it is more difficult to make a computation.
In my solution, there is both rotational movement and rotational movement around the vertical line and around it. So it's a spiral movement. There is helicity also. It's topological.
This could be something that I can try. Yes.
Okay,
thank you very much.
So just in your main theorem, you have big distance and you see that units, or
no.
You have this smoothing effect on the vorticity, and theorem criteria is not enough.
No, it's not enough, or at least I tried, but it is
the conservation of the energy.
No. What is what is nice that you have the conservation of energy, because the theory of monotone operators is using the test function as a velocity itself. So it is a real equality. But the fact the uniqueness may be
the smoothing effect on the
to tell the truth, I asked the student to do this, but he finished and then he didn't try. But it could work. Yes, you're right. At least for p larger than 3. Maybe p equal to 3 is not enough.
And for classical solution,
Yes.
Comments? Questions? Thanks again.
Thank you very much.
Thank you. So I'm still here tomorrow.
Yeah, no, I'm leaving